is 3D bioprinting, what is the applications of 3D bioprinting, and primarily we'll try to focus on liver printing. Suppose if you are trying or intending to take up certain projects around organ level printing, we'll focus on liver first, and we'll also try to see certain examples of how we have implied 3D bioprinting at various customer sites. As ma'am has also mentioned about Dr. Falguni Pati, he has been working on cornea, right? So we'll also take you through certain applications around cornea that he has applied through 3D bioprinting. Now, to start with, we are a 3D bioprinting company based out of Bangalore. We delve into manufacturing 3D bioprinters, and we also have a second sector, which is basically 3D next big learning, where we spread awareness and also educate enthusiastic people, be it scientists, researchers, any clinician who would want to get into 3D bioprinting domain. The course is basically formulated for educating anyone who is interested to learn more about 3D bioprinting. Now, to start, what is a bioprinting process, and how do we make or define the process, right? Now, in the first step, the first step that you need to take is to design your bioink. First, biomaterials, cells, these formulate the whole composition of the bioink, right? Now, the biomaterial that you're going to select, be it gelatin, collagen, this depends upon the application that you're looking at. So the first step is formulating your bioink as per the requirement of your application. Second is printing. Now, once you have formulated your bioink, you know what cell type you're using, what biomaterial you're using. Now you need to define what structure you would want to print it in. Now, since we are out here dealing with organ level printing, or we're looking into applications which can also cater to those interests, we can take a lot of topographical scans of organs, right? Where you can decide what shape of print you would want to do. Any shape that you would want to print, it can be defined in the CAD software, which can be translated through the bioprinter into the patient's wound area. So all the shape, be it complicated, easy, can be catered into as per the requirement of the user or the application that you're looking into. Post that, once you have printed, you can obviously culture it and grow into a skin. Suppose this example that you're seeing here is an example of an skin that we had built in-house. This is a scaffold which had been taken out from the printer and then incubated under proper temperature and pressure. And then we got the skin that you see here on the third side. Now, this is the bioprinting process, right? Starting from formulating your ink, designing your scaffold, developing the G-codes to print in the bioprinter, and then post-printing, how are you basically supposed to incubate it, culture it, and etc. Now, why do we use bioprinting? The first reason, obviously, is bioprinting organs for transplantation. This is the overall objective or aim that we are looking at when we talk about 3D bioprinting. But definitely, when we're talking about organ transplantations, it would be wrong to say that it is already done or it is already achieved, because I think the research that is required to be done around organ level printing, it will take certain while. It will take a while to achieve that kind of functionality. But right now, people have already achieved physical similarity, where you can print heart of same shape. You can get those structural similarity through bioprinting. So definitely, it is a step-by-step process that you would be taking to achieve or to at least reach that particular goal. But people are all around the world, be it in India or globally, have already started working around it. And they have gained a lot of good results using bioprinting at tissue level and at organ level as well. Second is precise spatial positioning of cells. Now, since this is a machine control setup, if you see this machine, it has 3 axes, right? X, Y, and Z. Now, you can control where the cells has to be positioned and at what shape. You can control the deposition of cells in a certain shape as well. So, which is very difficult to do through hand pipetting or any manual method. So, this is again a very good importance or advantage of using a bioprinter over any traditional methods of culturing. Second is enhanced cell-to-cell interaction. So if you see in this image, the video that is getting played there, it's a grid shape, right? Now in that grid, the pores defined, so the pores that you see here can be defined by the user itself. How closely you want the cells to be placed if it has to be placed at a distance of 0.1 mm, 0.2 mm, or 0.3 mm, whatever is a requirement, you can define that spatial configuration of the cell that you're placing in that scaffold. This interaction of the cells, again, definitely plays a very major role in how the tissue post-printing is going to work or function. So this enhances the cell-to-cell interaction using 3D bioprinting technology. Now, suppose you're using one type of cell, but you want to use multiple cell types to achieve a particular tissue. Now, you have multiple extruder setups in the machine, which allows you to use 2, 3, up to 4 different types of cells, types, or biomaterials in a same construct, defining each layer with a different kind of biomaterial. Suppose you are printing a particular scaffold of 10 layers, and you want the first 2 or 3 layers to be with a certain biomaterial or a certain cell type. You can define it through the software, how many cell types you want to use for printing how many cell layers. So all these kind of control or automation that you can get through 3D bioprinting is going to help you print any kind of complex architectures using multi-cell types in a single scaffold. Now, next, if we look into the next point, which is scaled manufacturing of human tissues as alternative testing models. Now, a lot of tests are done on animal models, right? Whereas we can eradicate that whole process of animal testing and define our own tissue models, which can be used for those testing purposes. Because we are using cells and printing these kind of structures, we can have a proper tissue model which can be defined for a particular application or testing purpose solely. So this can totally eradicate the use of animal testing that we are doing currently in any kind of clinical trials phases. Now, what is a bioink? Bioink comprises of biomaterials, growth factors, and any kind of cells. Now, cells have to be encapsulated around a proper bioink, biomaterial. Now, this cells has to be surviving throughout the process of your printing. Now, when you're putting the cell inside the syringe, it has to be extruded from the needle, right? It will go under certain cell stress. So to minimize that cell stress on the cells, you have to ensure what kind of gauge you're using, what kind of pressure you're using. But also out here, the material plays a very important role. The material should be giving a habitable environment for the cells to survive, proliferate, and grow inside happily, right? So that's where the choice of polymer that you are going to do for developing your bioink is very crucial here. Now, once your bioink is developed, you can start definitely printing. But the bioink optimization step is very crucial because out here, if you see here, the composition of a bioink comprises of biomaterial, cells, and bioactive molecules, which I said. Now, the property of the bioink, which will be defined by the viscosity of the ink, which will be defined by the viscoelastic nature of the ink, this all will define the printability of the ink that you're going to make. Now, if the ink that you have made is of very high viscous, let's assume, it will not extrude out from the needle, and neither will it form a proper shape in the bed. Now, if it is not able to achieve a proper shape, definitely you will not be able to achieve any organelle level shape or structure that you intend to make. You need to make your bioink of a certain optimal viscosity, which will enable you to print well. And also, once you're printing, it should be able to hold structure. So mechanical integrity of the bioink post-printing is also very important. Now, the printability out here, as I was saying, is defined by the viscosity of the bioink, by the viscoelastic nature of the bioink, shear thinning, and extrudability of the bioink. Now, these all parameters define if the ink that you have prepared is good to go for the next step or not. So out here, the bioink optimization step is involved. Now, second, when you're adding cell into it, right? How is the cell behavior in the bioink? Now, if it is biocompatible or not, if there's cell adhesion happening or not, if there's proliferation in the cell happening or not, those all will be catered by the biomaterial that you're using along with the cells in the bioink. So these are the very important points that you need to remember while you are making your bioink. Next, definitely, is the mechanical property that I was saying. Now, if you are, suppose, let's take Dr. Falgunipati's example. He's making cornea, right? Now, if in the cornea, I am not making the material stable enough that it can even hold the sutures then what's the point of even developing the cornea or printing it? So how do I ensure that it has mechanical stability? Is by choosing the polymers correctly, which will be giving the mechanical strength to the cornea that is getting printed. And obviously it should make the cells habitable. It should give that habitable environment for the cells to survive in it. So those properties are going to be very crucial in the early steps where you are defining what material you're going to use for the cells to be printed. Now, next, if you look into the type of biomaterials, definitely there are a lot of biomaterial options that you can choose from, natural, synthetic, depending upon what kind of cells you're again choosing, you have to decide what kind of polymers you would want to use for your application. Now, if we look into specifically one particular organ, which is hepatic engineering, just for example, these are the commonly used biomaterial and their complementary cell types. So there are a lot of researches that have already happened in the field of liver tissue engineering. If you see here, the biomaterials that they have primarily used are alginate, collagen, PCl, liver DCM, then again collagen, gelatin, a blend of that, blend of gelatin, collagen, and PCl. Along with the cell types, if you see primary hepatocytes, they have used with alginate. Then they have used Hep G2 with liver DECM. So these all combinations have already been tried and tested, and they have multiple applications that they have tested on using these particular combinations. Either they have printed certain grid shapes, certain liver or structural shapes where they have seen the interaction of these cells, how are they growing, how are they proliferating. We'll also delve into the applications using this particular gels in the next slides. Now, if you see here, these are the preclinical trials which are already being done on 3D bioprinting of liver. So if you see here, the bioprinting methods are categorized into two types. One is extrusion-based and one is liver-based, light-based extrusion method. So liver-based are these and light-based, right? So inject-based is also there one. So I'll quickly take you through what are these technologies as well. If you see here, there's a compressor which is attached beside the machine. That's a compressor which is basically providing air, compressed air inside the 3D bioprinter. So there's inlet and there's an outlet. The outlet is basically going to the extruder heads. So as and when we switch on the compressor, we can regulate how much pressure are we giving inside the extruder head. See here, there are two extruder heads that will be holding the syringe, the material inside the extruder. Yeah, you can maybe point it. Yeah, so you can point it to the compressor as well. I think you can just take them through, just point it. Anyway, after this, suppose this we have demonstration where we'll show it to you, but just show them the inlet and outlet quickly. So if you see, that's the compressor, right? Now the inlet into the machine, yeah, that's from where the compressed air goes inside the machine. And outside, if you can show the extruder heads also, Ashwini. So that's where the compressed air is going to keep going inside the syringe. Now your material that you're going to use is already loaded in the syringe. The compressed air will basically be the driving force for pushing out the material from the syringe. The needle that you see right now is 25 gauge. We can use any variety of gauge that you would want to use depending on the cell size that you're choosing to work with. So obviously, right now you can control the pressure also. You can see monitors, you can see regulators on top. Yeah, so that's how the extrusion method works. So this is called extrusion-based bioprinting, where you're extruding with the help of compressed air, and you can control the extrusion rate, flow rate, and everything. Now, this form of printing is called extrusion-based bioprinting. Another form of bioprinting is also there, which is called inject-based bioprinting. Now, inject-based bioprinting, what happens? The syringe setups that you see here is much more compact in that. There we have a piezoelectric element attached to it. Now, this machine that you're seeing is Trivima Advanced machine. This is the medium range of machine that you're seeing. In the next version of machine that we have the inject module already attached to it. So what happens there is the piezoelectric element will be attached to the extruder head inside, And as and when you give an electric impulse to the piezoelectric element, it will create a differential pressure inside the chamber. As in when it creates a differential pressure inside the chamber, it will extrude out one drop at a time from that inject method. Now, this kind of method is again used for organoid printing. When you want a controlled or specific volume of material to be dispensed, and you want to study this number of cell types that is going into that, the number of cells that is going into that dispensed droplet, and any other drug testing that you would want to do, you can do on that. So there are three types of technology. One is extrusion, inject, and then light-based. Light-based, again, is used via curing. So there are curable lights, like there'll be UV lights, which will be helping to cure the photocross-linkable materials that is provided in the material. So these three primary technologies are there, which you can use for your hepatic cell engineering. Now, if you look into the biomaterial section, you can see here sodium alginate cellulose nanocrystals, along with, again, primary hepatocytes or Hep-RG cells. So these are the combination that people have already tried out with, and they are already in vitro stage, preclinical trial stage. Now, if you are wanting to start any research from your side, you can definitely start with these references first, and then you can formulate your own ink by yourself. So these are tried and tested ink combinations that are already being applied in a lot of places. Now, if you're looking at some novelty that you would want to bring through your research work, you can try a combination from this section for your reference, and then later on develop your inks separately as well. Now, next, if you look at, so there are two separate ways that you can look into 3D printing and bioprinting. One is just via 3D printing without cells, and one is bioprinting, where you incorporate cells into it. Now, when you're looking at 3D printing, where you're not using cells, what you're getting is a replica of the shape and structure of any organ that you want to print. Now, post that, they'll not have any biological activity, but the applications that you can look at would be for medical education, would be for surgical planning, would be for simulating surgeries, and also for medical device training and research. Now, when you incorporate cells into it, it becomes a total different ballgame. Now, when you incorporate cells, it should be able to mimic the tissue microenvironment. Suppose you're printing liver, it should be able to replicate the liver tissue microenvironment that we see in the natural body to what we have printed in the artificial system, right? It should be able to replicate the tissue structure. It should be biologically active. So these are what we can achieve by developing any bioactive tissue models through 3D bioprinting. Now, the applications that we can look at through 3D bioprinting would be testing in cell therapy, doing some drug screening, disease modeling, regeneration and transplantation processes. So if we talk about some realistic applications that people are doing all across the world, if you can see, the first application is to compare drug sensitivity across 2D models and 3D models. So a lot of people start with 2D modeling, right? Just monolayer cell culturing. So you can compare how the 3D models are reacting and how the 2D models are reacting when you're incorporating cells into it. So these kind of studies have already been done. So liver on a chip is again a very innovative and a very eye-catching technology that people are actually working on right now. In this liver on chip, what you can do is you can create an artificial liver microenvironment inside a chip kind of setup, and you can do a lot of drug screening and drug testing inside that chip itself. Then definitely regeneration of damaged liver tissues, fabricating liver scaffolds with vascular formations, investigating the effect of hole size and angle between these lines of cells. So whenever you're printing any scaffold, each scaffold will behave very differently, depending upon what is the size that you were, what is the distance that you're maintaining between the lines or the scaffolds that you're drawing. So in those situations, what happens is every scaffold will behave differently with different cell type that you're using. So you can do studies around that as well. Post that, exploring the effect of ECM on mechanical properties and biocompatibility of the material. So definitely mechanical property out here is very, very crucial, because since you're going to look at in vivo transplantation, then the mechanical property of the scaffold that you're printing is very, very vital and crucial post-printing as well. Then obviously the last is bioprinted liver model to model liver injury leading to fibrosis. So a lot of work is already being done around this particular application. and around liver specifically. But if you look into the overall view, people are not only focusing on liver, there are multiple organs that people are also focusing at. In Indian research ecosystem, if I just take you through quickly all the other institutes who are already working in this, we have obviously Dr. Bhiman Mandal from IIT Guwahati. We have Sri Chitra Thirunal, who are working on skin and bone. Dr. Bhiman Mandal was also working on cartilage, skin, pancreas, and he has also, I think, achieved a lot of, gone up to preclinical stages with respect to a lot of cartilage formations. Then we have Dr. Jayesh Ballari from IIT Bombay, who has been working on bone tissue engineering. In KGMU, which is King George Medical College, Lucknow, Dr. Divya was working on bone. In Shastra, they have been working on liver and wound healing already. VIT University has already been working on wound healing and tumors. Now, if you look at global scale research institutes where people are already working in 3D bioprinting, you would see that Stanford University, Wake Forest University, UCL London, they're already working on cardiac, clinical, and muscle applications of bioprinting. So these are applications where people are already started to do a lot of research and also get a lot of good results in return through bioprinting. Post this again, we have Tel Aviv University who have printed a miniature heart. We'll take you through those videos as well, post this, where they have actually achieved proper structural similarity of a rabbit heart, and they could show it properly, in a vessel that they have printed. Let's go through the videos quickly. So this is Tel Aviv University that I was saying. Yeah, it's working. Yeah, so if you see here, yeah, no, audio is not there. Yeah, so if you see here, this is how the printing is happening. So this is a container which will have the biomaterial already into it, and the extruder will have a biomaterial type 2, suppose, which is a cross-linker kind of thing. Now, you are printing the cross-linker directly into the vessel, which already has a bioactive material. As soon as the cross-linker comes in contact with the respective biomaterial, suppose out here is sodium alginate and calcium chloride. They cross-link well, right? Now, if the calcium chloride is in the syringe and you're extruding out into the vessel, which has sodium alginate, as soon as the calcium chloride comes in contact with sodium alginate, whatever shape you have given through the printer, basically, it will be printing already in that fashion. And as soon as the contact happens, the cross-linked polymer will all settle in that particular shape that you have already printed. So let's just quickly look at this video. This is the miniature of rabbit heart that they have printed in Tel Aviv University. This is not using cells. This is where they have just tried to attain a structural similarity with the rabbit heart to see if the shape is attained, if it is cross-linking properly or not, if the mechanical integrity is there of the scaffold or not. So this is one of the examples. Next example that you see. So yeah, that was the 3D model. Now, next example, if you see here, this is in Rice University, where they have tried to bioprint alveoli. Now, this is, again, the pulsating thing that you see here is going to basically allow the red color ink that you see, which is basically what they're trying to replicate or mimic here as blood, is going to pass on through the vessels around the whole alveoli. So the functionality could be achieved here. In the first video, you could see only the structural similarity that they achieved. In this, they could also achieve the functional, they could mimic the functionality of that particular tissue, right? Now, this is also through bioprinting. Then another form, which is called volumetric bioprinting. Volumetric bioprinting is another, like extrusion I spoke, like inkjet and light-based bioprinting. There's another form of printing called volumetric bioprinting. Using that volumetric bioprinting, they achieved this kind of pulsating nature in the alveoli. Yeah, this is the example from Dr. Pati's lab at IIT Hyderabad, where he had printed cornea, and you can see him see basically a surgeon suturing the cornea into the lens, right? So this translucent material that you see, he is putting up, pulling up, trying to suture. That is what they have bioprinted as cornea. They could get a proper sheath. They developed their own bioink. It was not formulated or taken from anywhere. They came up with their own bioink that they would want to print. They polymerized it, and then they got a proper mechanically stable cornea, which they again transplanted it. If you see here, he is suturing it. Now, to get this suturing thing done, you need to ensure that the mechanical strength of the ink or the scaffold that you're having post printing is strong enough to hold that stretch, that stress in itself. Yeah. So yes. So this is the applications and obviously the little bit of the technology. Post this, we would want to show you a demonstration of the machine and also explain you what are the components in the machine, what are the features that you can explore, how do you get to print any shape that you would want to print. We are anyway having a workshop where we are going to show in details from 3D designing to printing in the machine. Right now, we have already prepared some prints for you. I think Anushri will take you through the machine, all the components of the machine, and also show you a quick print. If you want, you can come ahead and take a look in some time until before that, she'll just quickly explain the machine. A laptop. Laptop.
Yeah. So give me two. So good afternoon, everyone. Good afternoon, everyone. So this is our 3D bioprinter. Our 3D bioprinters are called Trivima, which in Sanskrit means three-dimensional. So this is the Trivima Advanced, which is our mid-variant range of bioprinter. We have several bioprinters depending on what technology is being used. In the Trivima Advanced, we use pneumatic micro extrusion based technology. So to break that down, pneumatic means with the help of compressed air. So that compressed air is supplied through this compressor over here. We have a compressed air that supplies sterile compressed air to the printer. And as Ankita mentioned it, this compressed air is supplied to the top of the extruder over here. So these extruders have an adapter onto which there's compressed air that is supplied, and this extrudes the bioink through the syringe out of the needle that is over here. So once extruded, this is printed onto the platform. The compressed air that is supplied to the bioprinter is controlled using these manual pressure gauges. So with this, you would be able to rotate and control the precise pressure at which compressed air is supplied, which would define the kind of bioink or the amount of bioink that will be bioprinted onto the print bed. So in the Trivima Advanced, we have 3 extruder heads over here. These 3 extruder heads have 3 pressure gauges that are linked to it. So with each of these pressure gauges, you would be able to control the pressure of air that is being supplied to each of these extruder heads. Now these extruder heads come with a magnetic head over here, which means it is swappable. So you would be able to print up to 3 biomaterials with 3 different inks and 3 different cells at the same time or simultaneously. So with these swappable extruder heads, you would be easily be able to interchange all of these extruder heads without much complication. Now coming to these extruder heads over here, these are dual mode temperature controlled. So that means you would be able to operate it from 8 degrees up to 60 degrees Celsius. The reason behind having a temperature control is different bioinks operate at different temperatures. For example, if you're using a biomaterial containing alginate, for example, that would need around say 30 to 35 degrees Celsius for it to flow easily through the needle to form a specific structure. Whereas there are other different biomaterials. For example, if you're using a bioceramic slurry, you would need a higher temperature. For example, if you're using a synthetic polymer such as polycaprolactone, you would need close to 60 degrees Celsius for bioprinting that. So depending on what biomaterial you're using, what bioink you're using, you would have to set that temperature on the extruder heads before printing. Now this is the print bed. So this is basically, as the name suggests, it is the bed onto which you print your bioink, right? So this print bed is also temperature controlled. So this print bed has temperature control from 4 degrees up to 80 degrees Celsius. So that is utilized in certain hydrogels that can be thermally cross-linked. So you would need heat for the hydrogel to solidify, for it to increase its mechanical integrity and retain its shape. In those cases, you would need the print bed also to have a certain temperature at which it should be set before printing. So I have spoken about the temperature control of the extruder heads. I've spoken about the temperature control of the print bed over here. Now, as you can see that the print head moves in the X and Y direction and the print bed moves in the Z direction. So this X, Y and Z motion ensures a 3-dimensional object to be printed. So that is the whole concept behind the bioprinting and behind Trivima as well. Now, when I spoke about control or how to control the movement in this bioprinter, that happens through our software here. So this software is our in-house developed software called Niyantranam. Niyantranam in Sanskrit means control. So you would be able to control all of the features in this bioprinter using the software. It is a very user-friendly software developed for everyone to use it, not just engineers, doctors, clinicians, students, researchers, everyone would be easily be able to use this software. So over here, if yeah, we are able to see the software. So this is called job control area. So you can see plus x plus y minus y. So that is the x, y, and z motion. Yeah. So this x, y, and z motion ensures your print to be controlled in the machine through this software. And the software also has other features that I will come through when we go through the demonstration in detail. So this is about how the software controls the 3D bioprinter. But we have spoken about bioprinting and printing with cells and all of that. So how do we actually print with cells? Or how is a 3D bioprinter different from a 3D printer? So that difference comes through sterility. So ensuring that there is a sterile environment for your cells to be printed in. How is that ensured is our 3D bioprinters come with a germicidal UV lamp that is at the top over here. I'll just turn that on in a second. We have a germicidal UV lamp over here. So once this UV lamp is actually set with a sensor over here. So once I open it, the UV lamp shuts down because UV rays are pretty harmful for us. So once you close the bioprinter, this UV lamp turns on. So ideally before bioprinting, you would turn on this UV lamp for about 30 minutes to ensure everything is sterile inside the bioprinter before bioprint. So once you turn on the UV lamp and you finish sterilizing, you would turn it off. And once that is done, you turn on the HEPA filter, which is the H14 generation of HEPA filter that we have installed in our bioprinters. So if you are able to hear that whirring sort of a sound, which mimics what happens inside your biosafety cabinet, basically. This is the H14 HEPA filter that's fit at the top of the machine over here. So this is how you would ensure sterility in the bioprinter for your cells to be printed. And this is about our whole bio.
You can control the volume. So volume, how much you are printing. Yes, and at what shape you would want the material to be printed. Suppose the cornea is there, right, sir? So in that cornea, I need to have a conical shape, a spherical dome kind of shape, a little bit elliptical as well.
So you print a scaffold on top of it, then you add the cells, or it there by
No,
layer
sir.
to the
In this material that you see, cells will already be fed in.
Oh, so cells
Yes.
fed in and the scaffold.
Yes, yes. So the material, suppose right now I'm using Pulmonic, what I'll do is, or suppose the ink that I am going to use for cornea, I already have the ink optimized. I'll add the cells into the ink and I can print. So what will have, the cells will already be encapsulated with the biomaterial as and when you print it. That's how it's.
Trying to demo here.
Yeah, this is synthetic polymer, Puronic. This is without cells.
Without cells.
Without cells. Just a synthetic polymer, which we are trying to print here. It's a little complicated structure. We have specially got this design for showing the globular structure through complicated design patterns.
Sumana must be interested in this.
Yeah. So if you want, you can come closely
You can
and
come,
take.
yeah. We have designed a simple globule structure to be 3D printed. So you can see it has that hexagonal
So any shape
structure.
that you would want to print, you can achieve. Be it a. Yes. So first step, we don't add cells because one, definitely it's economically expensive. Yeah. First, you optimize without the cells. Then you get the material property correct, because the printability out here is going to be the first big challenge that you're going to face, because not all materials are going to print this smoothly. This
But
is.
how
yeah.
do you plan the distribution of the cells within the different types of cells?
So it is going to be homogeneous, sir.
It's going
And
to be homogeneous.
yeah, but you can define it.
anyone's
you can define
interested
it
to
layer
have a
on
look
layer.
at the
So suppose
bioprinting, then
one
please
ink,
come ahead.
you have a certain concentration or certain density of cells that you have given in ink A. Now that is through extruder 1, but you can give a lower or higher cell density in the extruder 2. What you can do is 2 layers you printed with cell A, ink A. The second 2 or 3 layers you can print with cell type B. Or also you can design in a single layer.
How do you know that you're going to put it in the same place?
We can do that through software itself.
Like
You can define.
in the lobule you have
Yeah.
hepatocytes, you have everything else. No?
Yes.
Fibroblasts,
Yes, sir.
How do you manage what there in the liver?
Yeah, so suppose I have an article sketch. Yeah, sure. So, yeah, so yeah. So, ma'am has asked, suppose I want to print, ma'am, you can tell the question maybe.
My question was, so they are now printing the lobules of the liver. So in the liver, there are multiple different types of cell types are there. So how are they going to place these cells in the particular fashion that is actually there in the liver? We are trying to replicate a liver lobule, isn't it? So how do you manage to actually put it in that same way that the liver's lobule looks?
Yeah, so suppose in same layer, I want to use 2 types of cell types in a single layer print. I want 2 types of cells in a different localized areas. So there's a process called slicing that we have to go through to generate these kind of codes. So this is a 3D model. We do not directly put the 3D model in the printer. There's a step in between which is called slicing. In that slicing, what happens? Whatever 3D model you given, it will divide the 3D model into numerous layers and it will deal with one layer at a time. Now in that one layer, you can define which areas you want to use for which material. So that will be 2 different objects. So suppose lobules are there, right? The perimeter can be one object, the inside can be object 2. You can define object 1 to be printed with a particular cell type. Object 2, which is the inside part, can be printed with the second cell type. So all of this like defining and specifying which material should be printing which area of the design can be defined through that slicing software.
Like, have you worked on Procreate,
Procreate, yes.
iPad?
Yes.
Is it like that? Put one layer of paint and then you
Yeah.
want to show a 3-dimensional
Yeah.
image.
Yeah.
Like say you're doing a painting,
Yeah.
but you want to create looking more like a 3-dimensional. So there you use different layers.
Yeah, so you don't have to, so you design the 3D model first and then put it into the slicer software. The slicer software will do the rest of the work to divide it into multiple layers. You don't have to do it. Yeah, the software will itself do it.
So
You don't have
that
to
is giving
define.
it already. It is.
Yes, yes. Yeah, so that when you're dividing into layer by layer, so now that is defining the coordinates as well. So that's the function of the slicer software because this works on coordinate basis. You have to tell in terms of coordinate X, Y, and Z where you're supposed to move and extrude to get that particular shape. Now that work happens in the slicing software. So you just feed in the model, they will generate the code by itself. You have to just operate the interface accordingly. You have to put in the details and they will generate the code for you. Yeah.
Ink that you have,
Yes.
these are viable cells in
Yeah, BioWings has to be with viable
yeah,
cells.
viable cells.
Yes, sir.
Okay.
Yes, yes, sir.
And you sure that about viability of how long they stay outside in the syringe.
No, sir, it will definitely stay. That is for sure.
This curiosity will asking.
Yes,
So you have different types of cells in different
yes.
syringes.
Yes, and so this is where the optimization part comes in. So suppose you're using a particular cell, but you're giving a lot of pressure to it. So the cell death will happen inside the syringe itself. So you have to ensure that's where the optimization part comes in, that you use a minimum and minimum of pressure. You make your biomaterial, bio-ink that you're making very low viscous, not too high viscous, to have the cells encapsulated in it properly, so that with low pressure, you can extrude out and form whatever shape you would want to. Yeah, that is without cell. Obviously, in 80 degrees, the cells will not be working. So those are scaffold, like cell-free scaffolds. So you make the scaffolds, then on top you encapsulate, feed the cells. Yeah.
But where do you get these cells from?
So there are vendors, high media itself.
Oh, this is,
Yeah, they
this is
obviously.
from
Yeah, you can take it from there as well. Life of the machine, sir? Yeah. Yes.
That will depend on what biomaterial you're. Different biomaterials have different incubation rates. So that, yeah.
How long will that survive?
So,
Will the cell survive in that 3D mode?
yeah. Yeah.
So this, yeah, so ideally what happens is when you create these scaffolds and you incubate them in nutrient media, these cells will differentiate to form a specific tissue. So that tissue formation or that life that you're talking about will depend from tissue to tissue. For example, cartilage tissues takes about 6 to 8 weeks to form. So once that 6 to 8 week incubation period gets over, you will see that the cells would have differentiated to form a specific tissue. And the primary role behind a biomaterial is it provides that structure for the cells to thrive in until it forms that tissue.
The nutrient, the
It's like
growth
the
factors,
matrix.
everything
Yes,
will be,
exactly.
everything has to be incorporated in the bioink
Even in
itself.
cell culture, they used to use that matrix kind of
Yes,
thing and
yes.
then put hepatites into it.
Yes,
And then
the
they
matrix
start-
will be the bioink. That will be comprise the bioink that you're going to fabricate. Yeah. So, lot. I think it's not. Yeah, you would answer.
Introduce now, Mr. Piyush Padmanabhan is the principal person here. He is giving chance to his colleagues to talk.
What
Yes, sir.
stage are you in for this?
So I think it depends from, organ to organ. So if you're looking at cartilage, in New York, what they've done is they've 3D printed a cartilage for basically a condition where the ear wasn't completely grown. And they were able to actually create the entire ear in a PCL scaffold. So it's just a synthetic polymer. They just printed the outline of the cartilage and they wanted the skin to actually grow over it. So that was one of the applications. In AIMS in New Delhi right now, IIT Bombay, one of the professors who sort of is like a mentor to me, Dr. Jayesh Bellare, he has developed his own biomaterial that can be used for non-load bearing regions of the body. Basically, they are printing it and it's currently in phase 2A clinical trials at AIMS. You have Dr. Pati's work on the cornea, which is very well known in this part at least. And in
The
sorry,
cornea has been used actually.
so not us. So Dr. Pati has actually developed a biomaterial. What he's done is he has taken decellularized ECM and he's basically printed it in the form of a sheet. Now, once he's printed it, he's punched a hole through it, and basically that creates the roundness of the cornea. Now, to create the curvature, that's the struggle, right? You need to create the curvature and the elasticity of the cornea. Mimicking that is something that's quite difficult. So that's where they are working towards right now. How can you create the stiffness? So this is the biomaterial developed by them. So they were finally able to get the suturability of the biomaterial. So basically they are suturing it to see if it's actually tearing. In real cases, it shouldn't tear. So here they were able to get the stiffness, the mechanical stiffness that was required. This was done using making tweaks to the biomaterial. The process is same. They're using bioprinting to print those sheets, but then they're using, material science as well to actually get the stiffness of the biomaterial to make it suturable. And ideally, they would put it in the portion of the cornea and allow the cells to start taking over. It's printed without the cells. The cells will start taking over, and slowly this cloudy structure would actually become transparent. That's what they're aiming for. Mhm. 3D printed titanium implants, cobalt chromium implants, all of them have been used for. No, nothing living at the moment. No, nothing living at the moment because they're currently under trials. All of them are either in the preclinical or in the clinical phases. And most of them are working towards the resorbable portion, you know. So if you're looking at the cornea, specifically, he is going through preclinical right now. We have a college named Sri Chitra Tirunal, which came with the heart valve so many years ago. They are specifically working on the liver-based bioprinting, and they're creating smaller patches using a light-based biopolymer. And currently, they're doing some small rabbit and mouse-based testing, but they're soon planning to go into chimpanzees as well. So it would take another 3-4 years for us to get to clinical trials in that. But things are moving in the right direction. So there's a lot of research that's happening globally in this.
Is anybody working with blood vessels actually? Like, see, we use a lot of these graphs right now.
Yes.
So do you
Blood-
have any idea of bioprinted
Blood vessels, do you want
graphs,
the-
actually, blood vessel graphs?
Not a
Because
graph.
the transplant people use it a lot actually, and
Mhm.
we
Yes,
retrieve the
yes.
cadaver vessels and then use it for.
Okay. This I'm not aware of at the moment. It can be done.
Okay, I think we can
Probably,
work
yes.
with this. I
Yes.
think we can work with this tube because the commonest thing that we use on the surgical side can be translated
think-
usually the vascular graphs.
I think what we can do is if you can show that video of coaxial. So we have a mode of printing here called coaxial. So basically it's embedded. You're embedding one gel within another. So basically a tube, imagine a tube, but the inner portion of the tube is also filled with the gel. Imagine if you can actually make the inner gel sacrificial. So you can actually have a tube that is being printed. Now this is one layer, right? You can even go up to 2-3 layers more. There are triaxial, quadaxial applications where you can print with 4 different biomaterials. So what you see there is, I'll just move aside so everyone can see. Okay, it's the main screen. So you can see the transparent gel that is there, and then you have the purple color gel right in the middle. So that is actually getting printed within the transparent gel. So this is called coaxial bioprinting. This is done at Central Leather Research Institute in Chennai. Now we can go up to 3 different biomaterials. Now imagine another biomaterial coating this, or 4 different biomaterials. So you can print with multiple cell types if you even want to go to little more complex constructs as well. So that is where, with respect to this, there is a true sense of actually exploring something like this. Yes, yes. Yes, yes. So Shastra is working on esophageal cancer. That's what they told. Wound healing is that, and then they were also, I mean, we were applying for some projects, so that's how we know. So they are working on esophagals as well. So that is another application that they are focused. Oh, sorry. They are using our bioprinters actually to create bone-based applications and cartilage. So they're using our bioprinters for that. But apart from that, the rest of it is.
I think we should work with them actually to see if, I think we should work closely with them to see if we can at least the vessels, vascular grafts actually, those are the easiest ones which you can experiment, also try.
Yeah, we
Because
can.
we have an animal lab here. We can
Okay.
get the tissues from the rabbit actually. Suppose we give the material, maybe we can make the bio ink out of it.
Yeah, we can actually work on that. And I think we can get the right experts also to come on
tubeless,
board.
like
And
we have, we have the experts here.
okay.
And we have the labs here. I think maybe we can try doing some work actually.
Yes,
The
sir, sure,
tubulous
we can do
structures are
that.
the easiest ones to do. Even if you get a centimeter of the thing, actually, it makes a lot of sense.
Okay.
They are not able to bring in the curvature because it's not sort of stiff,
yeah.
right? The same thing would apply for anything. Like say you did a heart, will it stand? Like say, or is it collapsing because your the material that you're using is actually a polymer.
Yeah, dome-shaped structures are quite difficult to achieve using this. If you're using printing a pure dome like the cornea. So what they're doing is they're using light. So basically, imagine a cask if with biomaterial in it, you're exposing it to light, and the light actually exposes an image. And just imagine this is the curvature, slice it into layers. So each layer is getting exposed. And whenever the layer gets exposed, only that layer gets cured. The rest of the layers remain normal. And as it's forming, the entire curvature gets formed. That's how the entire concept of light-based works. So you're able to print those dome structures. But what they're saying is through extrusion base itself, they're able to get to that curvature. They're able to tweak the biomaterial to get that curvature. So there's something called 4D bioprinting, where the fourth dimension is time. So over a period of time, the material has memory flex. Basically, it flexes back to its original state. So that is another form of bioprinting. So we're doing that with BITS Goa currently, where they are actually printing the material and allowing it to change shape over a period of time.
All these things are actually already taken care of.
Yeah,
Like
so
say
there are
so many
multiple
questions we
strategies
have
to work.
had, and They're already working on it.
Yeah, yeah.
The two, one is
Yes.
the structure, other is the,
Yeah.
right? The structure obviously here by this,
Yes.
and what are the tip actually function? So
Mhm.
liver actually a range of,
Yeah.
how do you make
So the first thing we do is before the construct is printed, we check how viable are the cells. When you print these cells, they go through a syringe that is really tiny. Can you take one syringe out? So it goes through a syringe. So this is about 200 microns. Now imagine a bunch of cells going through a small syringe like this. What happens is the cells start to lose their viability when they go through so much stress and strain. So you're first understanding how the cells have been printed. So that is called the day 0 or day 1 test that we do. Then after that, you do a test after 2 to 3 days to understand the cell's migration. How is the cell migrating through the scaffold? How is it proliferating through the scaffold? So that's like the 3, 4, 5 day. You do that experiment. Then you understand if the biomaterial degradation rate is lesser than or equal to the rate of formation of the ECM, the extracellular matrix. So the biomaterial degrades and the extracellular matrix forms. So that rate has to be equal to or greater than. So you do that calculation. Once the tissue is completely formed, you do an H&E analysis to understand whether you're getting the proper segments within the structure. There are various other assays also that are done to understand that. After this, you do your confocal and a lot of different studies to understand where exactly what proteins are being expressed. Are the proteins being expressed properly? Genetic variability is also studied. That's another thing that is studied. Yeah, yeah.
how do you take a part?
Yeah, you take a
Material and
sample and do a study. So that is specifically how you do. So these are all the studies. We worked with skin internally in-house. So we printed the dermal and epidermal layers. So when we did that, these are all the tests, that battery of tests that we had to do. So you don't understand when the cells are put through all the strain, right? They go through certain mutations. You can never guess what will happen. So you have to account for that, as well as protein expressions can change when cells are put under different environments. So you're looking at how all of that changes. You don't understand what are the toxic byproducts that are produced during the degradation of your biomaterial. That is something that we study as well. A lot of factors that work. Yeah, so we do, like I said, genetic variability studies are always done. Mutation studies are done. So we understand the whole battery of what is exactly has to be done through. That's all done.
Guru,
Yeah,
Guru.
yeah.
So I'm continuing that question.
Mhm.
So viability is a big question. 3D printing.
Sorry?
So viability,
yeah, viability, yeah.
during the 3D printing. So most of the cases, gelatin or else alginate people are used
Hmm.
for 3D printing purpose.
Yes.
So the final thing is how cell crosstalk, proliferation,
Yeah.
or cell migration,
Yeah.
as you said, happen.
Mhm.
So it's a viscous solution or gelatin and all. So once just wanted to print or printed material, question will happen. Earlier,
Mhm. So when you're first, you have to calculate how many cells per square millimeter of the scaffold you want. You first understand that. You culture it to that level, and then you get those number of cells with the biomaterial, mixed with the biomaterial, and then you print, right? Now, with how do you calculate the number of cells per square millimeter? One more thing is that you understand the cell density in the in vivo tissue. So you understand that. So that is where you're taking the basis from. Number of cells per square millimeter, you take it from that, do your calculation. Then you understand, okay, these many cells I have to print. So that's where the machine allows you to control that through flow rate. Now, the cell-to-cell signaling is obviously taken care of because here the cells are layered in a three-dimensional space, not in a two-dimensional space. In our bodies, three-dimensional is what they are used to. So when you put them in an environment like that, you see an enhanced cell-to-cell signaling. That's why we moved all the way from monolayers to 2D and then now 3D, right? Our transition has been that because of this factor. Now, another thing that comes into play here is something called microporosity. where how porous, you said alginate and gelatin, right? All of them have something called microporosity, where is the distance between the pores, there are micropores that are there within the structure that is formed. So that those micropores allow the cells to move around. So the cells actually move within the scaffold. They're not stationary. You don't want your cells to be stationary. You want them to start interacting and moving. So that is where, the cell signaling plays an important role here as well, where it tells the cell, okay, you have a little more space, you can move in this direction or that direction. So that's something that you control through your microporosity. You have to do specific studies using scanning electron microscope to understand what is the microporosity that you're getting. For example, we were working with beta tricalcium phosphate, very commonly used for bone. When we were working with it, we printed these scaffolds, and we were able to we weren't able to understand why the cells were not adhering. The osteocytes were not adhering. So that what we went ahead and did, we did an SEM, and we understood that it was 120 microns. The microporosity was at 120. We needed it close to around 80, and that's when we had to play around with the biomaterial a little bit to make it work for us. So all of these play a very critical role in viability, uh, migration, proliferation. All of this plays a very, very important role. I hope.
Continue. There is any biomaterial allowing the for
So you're talking about any specific biomaterial that can
Yes.
be used across, right? So right now there is nothing like that that is found. If you find it, tell me. I'll. But right now, no one has found it, because we are all looking for that. We are all looking for that one biomaterial that works across cell types. See, you can find biomaterials that work for fibroblasts and keratinocytes. Same thing. The same thing applies across the spectrum, right? So that's where people are looking at what biomaterials can be used. But most commonly, people start with anything gelatin based because of the RJD motives. It works with a lot of cell types. So gelatin would be one place to start. But then, as you move into different aspects, you'll see that there is a lot more that you can do. There's a lot more biomaterials that you can explore. So one biomaterial that suits all, as of now, it's not found, but everybody is looking for one biomaterial that can at least serve 10 different cell types.
how sure about you are maintaining solution materials.
Yeah.
Gelatin challenges.
So we overcome that using two methods. One, we have certain mechanical fixtures which we have patents for in India, which basically allows for the movement. So if it goes from 1 to 1.1, if you give that signal, generally machines go to 1.1 to 1.13. So you're controlling that movement, right? So that's where you have some correction strategies that we put into place. And the second thing is we were talking about it in the morning. We are working with Microsoft on integration of artificial intelligence to correct for any errors that can happen. So when the error is happening in real time, the machine should be able to understand that yes, I'm making an error and correct for it within a microsecond. That is what we are training the machine to do. So currently we are working with Microsoft. Ankita is heading the project there. So we are working with Microsoft on that to make these machines a little more smarter so that they can go into the surgery room if need be as well. And it should be able to understand what changes are happening. And if there is a change that is not suitable for the procedure, it should change it immediately without even like within a microsecond, all that should happen. So that's how we train. Yeah, we are here all day. Yeah. Yeah, thank you.
Thank you so much. Thank you.